In the previous video, we introduced graphs and gave you basic information that you will need as we now begin to learn how to plot graphs in physics. In this video, we will start by learning how to determine the main scales of graphs, why good scales are important, and finally showing you what plotted graphs look like. Determining what scale you will use to plot your graph is a very crucial step. The important thing to first remember is that scales must be in multiples of 1s, 2s, or 5s. This concept does not only apply to the ones column, but can also apply in the hundreds or thousands column, such as 500 or 2000, as well as the tenths and hundreds column, such as 0.2 or 0.01. As you plot physics graphs, there will be situations where the scale is provided for you for both axes. However, there are also situations where you will be required to determine the scale for one or both axes. Therefore, let's become familiar with a formula which will allow you to determine the scale for every question without guessing, unnecessary erasing, and mistakes for each axis. The first thing to do is to determine the variable range. This is calculated by taking the largest data value in the table and subtracting the lowest data value. For the beginning stages of plotting, the focus will be on plotting from the origin. This means that the lowest data value will always, keyword always, be 0 regardless of what you observe in the table. The next step is to count or measure the number of centimeter blocks. This concept will be shown in detail later on in the video. Then, the scale is calculated by inputting the variable range over the number of centimeter blocks into a calculator. One more thing to note is that when using this formula, you always have to round up when it is not already a multiple of 1, 2, or 5, as normal rounding off rules do not apply. Finally, these three steps apply both to the x and y axes. So let's take a look at an example. The example states to plot a graph of mass, which will go on the y-axis, against volume, which will go on the x-axis. So let's start with the x-axis calculation. Based on the information given in the question, we know our focus will be on the volume section in the table. The first step to do is to find the variable range, which means it will be 40 minus 0. And please remember, since we know that we will be plotting from the origin, the lowest data value will be 0. Therefore, we get 40 centimeters cubed for the x-axis. The next step is to find the number of centimeter blocks on the graph paper you are using. For the graph paper used in this question, it was 18 centimeter blocks. Now let's just be sure you know how 18 centimeters were obtained. Before you can begin measuring, you need to be sure of the type of ruler that you have so that you are not introducing any more errors. The first type of ruler is where the 0 is directly at the edge of the ruler, which means that the edge of whatever you are measuring needs to line up with the edge of the ruler. The other type of ruler is where the 0 starts just off the edge of the ruler and the edge of what you are measuring needs to line up with the new 0. Once you have determined the type of ruler that you have, you will now be able to find the number of centimeter blocks on the x-axis. To do this, you line up the 0 line of the ruler with the beginning of the graph lines on the left-hand side horizontally. Where the graph lines match with a number on the ruler, you read off the number of centimeter blocks on the graph. For this graph paper, there are 18 centimeter blocks. When we return to the example, we understand how 18 centimeter blocks were obtained for the x-axis. We now move on to step 3, which is the scale calculation. This is 40 divided by 18. This gives 2.22 reoccurring in the calculator, and you may be tempted to round down to 2. However, remember, we said at the beginning, you always round up. So if you have to round up based on multiples of 1s, 2s, or 5s, we can therefore round up to 2.5, which is half of 5. But let's be sure why we always round up and not with normal rounding rules. The range which we calculated for this question was 40. And if we fall back to the usual estimation rule, the scale will end up going up in 2s. However, this is 2s for 18 centimeters. And when we take a look at the x-axis with that scale, the maximum value is 36. But you need to be able to plot up to 40, and you cannot suddenly decide that you will start plotting on the white space on the graph sheet. What you need to do now is to go back to the original plan of rounding up, and you observe that the maximum value which you get is 45. This value is more than enough for what you need for plotting. Now let's move on to the y-axis calculation. If we read the question again, it states that we are plotting mass against volume. This means that mass will be on the y-axis. Thus, we look at mass in the data table. Step 1 states that we calculate the largest data value minus the lowest data value, which is 40 minus 0. But you may be saying, wait, that is not correct, as 5 is the lowest data value in the table. But remember, we are plotting from the origin. So regardless of what the lowest value is in the table, the lowest data value for the calculation will always be 0. Step 2, we observe 25 centimeter blocks on the graph paper. And just again to confirm that you know how to measure the y-axis, we will go through that now. For the y-axis, the ruler is lined up vertically anywhere on the graph. You then line up the 0 with the top and read wherever the graph line ends at the bottom relative to the number that it lines up with on the ruler, or vice versa. In this situation, we observe 25 centimeter blocks. However, when it does not line up exactly with 25, as long as it is close, you can confirm by counting the centimeter blocks, which is about 5 lines by hand, and see that it will still match back up with 25. Another important point to note is that every graph is not the same, so what you may have on your graph paper in terms of the number of centimeter blocks may not match the example that I have here. So when we go back to the question now, we understand how 25 centimeter blocks were obtained. Step 3 is 40 divided by 25, which gives 1.6. But remember, we always round up, which gives us a scale of 2. When plotting graphs in physics, a single dot will no longer suffice. You either have to use a X or a dot with a circle around it. In the second step, what you can do is that after you have finished plotting, you may recognize that some points are extremely far off. Therefore, you check those points and make sure you have plotted those points correctly. And as long as you have plotted them correctly, then you move on. In step 3, because you are plotting from the origin, you will be starting at 0. However, just note you tend to plot from the origin when your aim is to prove linearity, extract data, or if the question states you should do so. And finally, you need a good graph which will cover the graph paper by at least half, which is okay. However, 3/4 is preferred. This can be done by using a portrait or landscape orientation. So you may be wondering, why is there such an emphasis on having a good scale? When you take a good look at this graph, it has a lot of white space. It does not follow the at least half rule, and extracting information from this graph would be very difficult. On the graph with the good scale, however, it occupies at least 3/4 of the graph paper, and getting information such as the gradient would be a lot easier. The website where I found these pictures also has very good examples of graphs which you should not be plotting, so I will link that in the description below. So let's move on to taking a look at the plotted graph. This particular graph was plotted using software, but in the next slide you will also see what it will look like if graph paper was used. But let's take a good look at this graph first. We have labeled the axis with mass/grams and volume/centimeter cube. We also ensured that we have placed the scale carefully on both the x and y axis. Therefore, on your x-axis it goes 0, 2.5, 5, and 7.5, etc. And for your y-axis it goes 0, 2, 4, 6, etc. If you recognize, these scales go up in equal amounts. So you do not just take the values you have in your data table and put them as the scale for your graph. It has to be equal intervals. Once you have done these first set of steps, you proceed to plot. For this example, the points from the data table were plotted using x's, and then your best fit line was done. Now we will see what the graph looks like on graph paper versus plotting it with software. What you can recognize is that it looks a little different, and this could simply be due to spacing. This will also let you know that depending on the graph paper that you have, your plot could look different to someone else's. So your aim is to ensure that you have followed the correct steps so that you will always have the correct graph. Now let's take a closer look at the x-axis, and you will see it is now going up in 5s per centimeter. Previously, it was going up in 2.5s per centimeter, and you may be wondering, why did we do this? When you take a look at the volume data given in the table, you recognize there are no 0.5s of any of the values in the table. So what you can do is double the scale. This means you take 2.5, multiply it by 2 to get 5, and you take 1 centimeter, multiply it by 2 to get 2 centimeters. So while the scale is ultimately the same, you now have 5 centimeters cubed for every 2 centimeters versus 2.5 centimeters cubed for every centimeter. I want to thank you all for watching this video, and I hope that plotting graphs is making a lot more sense to you now. In the next video, we will be breaking down the lines of the centimeter block, looking at the best fit line, and analyzing graphs to get information such as the gradient.